Okay, so our last talk of this session is on multi-hop knowledge graph reasoning with reward shaping, and the speaker is Victoria Lin from Salesforce.
Hi, everyone. Thanks for coming. I'm Victoria Lin. Today, I'm going to talk about how to train a model to answer knowledge graph queries which require multi-hop reasoning using reinforcement learning. This is joint work with Richard Socher and Caiming Xiong from Salesforce. What motivates this work is that we believe in the future, question answering is going to be the dominant way for people to interact with their computing devices. Computers have access to different types of resources to answer these questions, such as text, images, knowledge graphs, etc. Among these, knowledge graphs are especially useful to model relations between entities among a certain domain, and also perform automatic logical reasoning on top of those. So for example, the user might ask a question, which directors has Tom Hanks collaborated with? The computer could recognize the structured query from the question, and also recognize that the answers to this question will be some entities that it can look up in knowledge graph. Throughout this work, we suppose that the structured query has already been parsed, and we focus on how to effectively retrieve the answers from the knowledge graph. In practice, a knowledge graph we encounter may look like this. It contains missing facts because knowledge graphs are intrinsically incomplete. Hence, to correctly answer the question, one needs to resort to techniques such as link completion or explicitly reasoning over the discrete structure of the graph. Knowledge graph embeddings is a commonly used technique for link completion. These techniques assign vector representations to the entities and relations in the knowledge graph and use them to parameterize a likelihood function for the facts. A trained function could be used to estimate the likelihood for facts that does not exist in the knowledge graph. State-of-the-art models such as COM-E use standard neural network operators to parameterize this function. And these type of models achieve high accuracy on standard benchmark data sets despite of being very simple. However, they are not very interpretable because all they can produce us is just a likelihood score. To account for interpretability, an alternative approach is to directly reasoning over the discrete graph structure. We call it multi-hop reasoning models. What's interesting about these kind of models is that they can be formulated as a sequential decision process. So given the structured query and the topic entity, such model can be trained to sequentially expand its inference path until it reaches a correct answer. Recent work Das et al. Shows that we can use reinforcement learning to train models to perform this type of sequential reasoning. This approach is interpretable. However, on standard benchmark datasets, they have shown significant performance gap compared to knowledge graph embeddings. In the ideal case, we would prefer something which is both interpretable but also perform competitively. To gain some insights on how we could modify reinforcement learning training to achieve such goal, let's examine some challenges which makes reinforcement learning training particularly difficult in this case. The first challenge is caused by knowledge graph incompleteness. So because the knowledge graph contains missing facts, during training time, if our model extends the reasoning path to a correct answer which does not exist in the graph, it will not receive any reward. Therefore, the parameters will tend to overfit to only the observed answers in the graph. Secondly, between most pairs of entities in the graph, there can be multiple paths connecting them. However, not all paths are equally predictive for the relation in question. For example, as shown here, path 1 and 2 is not very predictive for the collaborator relation. However, in knowledge graph, most of the cases, there will be far more spurious paths compared to those logical, make sense ones. Hence, the model will have tendencies to overfit to those paths and hurts its generalization at test time. In our work, we propose two techniques, reward shaping and action dropout, to account for the challenges mentioned above. Our technique is integrated with a standard policy gradient algorithm. Before introducing our technique, let's first take a quick deep dive of a standard formulation of policy gradient. A reinforcement learning framework can be described by the following components. In our setup, the environment is the entire knowledge graph, plus the structured query issued by the user. A state is simply a node in the knowledge graph, and also in our model, we constantly incorporate the structured query as part of the state definition. The actions are simply the edges outgoing from the current node. And to perform an action, the agent basically selects an edge and transits to the entity on the other side. It performed this type of transition for a maximum number of t steps, and the entity it reached at the last step is used as the predicted answer. If the predicted answer is observed as a correct answer, the agent receives a positive reward, 1. Otherwise, it receives nothing, so we use a discrete type of reward. Given this framework, policy gradient can be used to model which action to choose given a state. So the key component of policy gradient algorithm is a policy function pi theta, which defines the probability of choosing an action given the current state. In our work, we use deep reinforcement learning to parameterize this policy function. I will not go into the detail of this graph, and please check our paper for the exact formulation. However, I would like to point out that for our contribution, the exact parameterization of pi theta doesn't matter. Our model extension are applicable to basically arbitrary parameterization of pi theta. Pi theta can be trained using the standard reinforced algorithm. Given the structure query and the topic entity, reinforced algorithm sample inference paths based on pi theta. It observes the reward and then updates theta by maximizing the expected reward. Here we immediately notice a problem caused by graph incompleteness, because although Steven Spielberg is a collaborator of Tom Hanks, it is not observed in knowledge graph, therefore it cannot receive any reward. Not only will this type of false negatives cause problem, but for a lot of queries, some entities are more related to the correct answer than the others, but the current rewarding scheme is penalizing them all equally. So our reward shaping technique is basically wants to introduce the notion of soft correctness to the reward scheme. For the entities returned whose correctness cannot be determined, we introduce a continuous function f theta to estimate its correctness. F theta takes the topic entity, topic relation, and also the entity returns by search as an input and estimate a scalar correctness. We intend to keep the form of f theta general, so one can basically use anything that performs well here. So here, notice is the connection of its form to the knowledge graph embedding functions. Actually, in our work, we use a pre-trained ConV model to estimate this correctness. ConV model is a state-of-the-art knowledge graph embedding model. And for the answers whose correctness can be determined by knowledge graph, we still keep the original positive reward. This is how we solve the graph incompleteness problem. And we still have the path diversity problem to deal with. So for this problem, because there is no access to direct supervision, at first glance, it seems that there's not much we can do about it. But I think the intuition here is we want to prevent an agent from repetitively selecting an action that has received a reward before. So what does it mean? Like, look at a training snapshot for illustration. So at this time point of training, the second action is more likely to be selected. It has a sampling probability of 0.6 because of previous update. The action dropout technique is inspired by the dropout techniques used to prevent neural network training from overfitting. And what we do is we randomly offset the probability of certain actions to 0 and renormalize the policy function. So now we obtain a new policy function, pi tilde. And according to this policy function, the first action has a larger probability to be sampled. Therefore, we effectively encourage the agent to explore the first action, although initially it has only a tiny probability to be sampled. By using this technique in practice, we could encourage the agent to explore up to 8 times more paths during training. And by exploring more paths, it significantly reduces its chance to overfit to a specific path. This is how we solve the path diversity problem. So we test our proposed techniques on standard knowledge graph benchmark datasets, and we use 5 of them. So the knowledge graphs here comes in different sizes as well as different graph properties. And here we specifically solve them according to decreasing connectivity, so they become more and more sparse. We use a ranking-based evaluation protocol, mean reciprocal rank, so it is the higher, the better. To show the contribution of our proposed technique, we first show the result of an ablation study we done on the dev set. So here shows the vanilla policy gradient on all of the data sets. By introducing each of the techniques alone, we observe improvements on most of the data sets already. And here it seems that action dropout is more effective. If we introduce the 2 techniques at the same time, they could interact with each other positively, and we got the best performance most of the time. It seems that our techniques in general performs better on graphs which are densely connected. We have a detailed error analysis in the paper, and please check those out. And also, you're welcome to ask me questions regarding that. To set the result in a wider context, for the main result, we compared with state-of-the-art multi-hop reasoning approaches and embedding-based approaches on the test set. So here, the dark blue bar in the middle is our approach. The blue bars to the left refers to the multi-hop reasoning baselines. And the little hourglasses here actually indicates a model that hasn't finished training within a certain time threshold. So some of the previously proposed multi-hop reasoning approach doesn't scale well to larger data sets. And here we show that our model basically successfully improved the state-of-the-art multi-hop reasoning performance on most of the benchmarks. The yellow and orange bars on the right are the performance of the knowledge graph embedding models. We see that in general, the performance is higher compared to the multi-hop reasoning models. Our model basically is the first one that consistently matches the state-of-the-art knowledge graph embedding performance on most of the data sets. So lastly, I would like to show a qualitative result. So here shows a query we sampled from the dev set. So the query basically asks for this person called Laura Carmichael, what is the profession of her? And here we visualize the unique top 5 entities retrieved by our reinforcement learning algorithm, as well as the path that has the highest scores, which leads to each of the entity. The darker orange entity is the correct answer. The lighter orange entity is the wrong answers. The search trace together, they form a little subgraph, which could give some insights. So here we see that the model successfully captured the insights that to infer the profession of a particular person, one could infer that based on the profession of the people who are related to them. And especially here, our model successfully captured the relation award by ensemble, which means that the two persons has won the same award during their career. Therefore, they are likely to be in the same profession. And as an interesting fact, so most of the entities shown here are cast members from the British television show Downton Abbey. So with that, I would like to conclude my talk. So in this talk, I introduced the two techniques, reward shaping and action dropout, which is used to improve reinforcement learning for multi-hop knowledge graph reasoning. Our approach significantly improved state-of-the-art of multi-hop reasoning performance on benchmark datasets, and is the first one which consistently matched knowledge graph embedding performance on a variety of datasets. For future directions, we would like to learn better reward shaping functions, because here we are using pre-trained functions. And in the future, we want to see if we could jointly learn that. And also, we want to investigate if similar techniques will be suitable for other RL paradigms, such as Q-learning. Of course, we also want to extend the model to answer more complicated structured queries, as well as natural language questions. Thanks. I'm happy to take any questions.
Hey, thank you very much for the talk. I was wondering that it seems that a lot of your problems are kind of caused by noisiness in the knowledge base. So would it be possible to actually use your technique to improve the knowledge base and clean up some of the things?
Okay, so the question is like, could our technique help to improve the knowledge base and clean out noises? I think it's possible. So I think for our techniques to improve knowledge base, what it happens is like we could run multi-hop reasoning using our technique, and that will generate new facts. And so probably the new facts could be added to the knowledge graph. Also, like for existing facts, probably we can use that to verify. So actually, one thing interesting is like, So given the technique, so for example, for a pair of entities in the graph, you can use our technique to search for the reasoning path and check whether that makes sense or not. So that's also a way to help improve the knowledge base. Thanks.
Hi, thanks for the great talk. I have a question about the interpretability. Did you evaluate it quantitatively or qualitatively?
Qualitatively. So we basically we took the queries and showed the path and just eyeball whether the path is reasonable or not. So we didn't adopt quantitative evaluation for interpretability.
I see. Thanks.
It'd be interesting to see that. Yeah.
Okay. Yeah, can you come to the mic, please?
Thank you for the really interesting talk. I was wondering whether you have any insight on the effect of the length of, well, the number of hops on the accuracy of your model, so in particular against conv, but also in general, are there some facts that require many hops, or are most of the facts just reachable within 1 or 2 hops? Thank you.
Thanks. So the question is like whether number of hops will have, what's the effect of number of hops on the performance? So I think in our experiments, as well as like the previous work, actually number of hops is treated as a hyperparameter. So the performance could be sensitive to that. So on 5 of the knowledge graphs, I think we use a 2-hop inference, some we use a 3-hop inference. So hop will matters, but like above 3-hop, actually we try that. It doesn't show significant improvement. And also I think one possible explanation for that is depends on the benchmark, the quality of the benchmark we have. So maybe the current benchmark gathered for a lot of entities, if you cannot reach those outside 3 hops, it means that they actually don't have much relations in between. But like the high-level suggestion is like treat number of hops as a hyperparameter. Thanks.
Okay, I have one question.
Sure.
So do you have any comments on, or whether you tried like, using the pre-trained embeddings and like the conv and all to maybe densify the knowledge graph first and then run your approach on top of that?
That's such an interesting idea. Yes, I think that's an interesting thing to try. We didn't try that, but yeah, so basically if you will have like a knowledge graph embedding, first complete the graph and then run paths. The problem with that is, in this case, if when you are doing this, when you are generating paths, your path will consist both like the sure edges and also edges which you are not quite sure. So it contains a mixture of actual edges and virtual edges. Right. That will affect interpretability a little bit. So, but I think that's something interesting. Maybe it will improve the results.
So maybe you can still have different markers for those 2 relations.
Right, right.
Then,
right. Some comes from the knowledge graph embedding.
Right,
yeah.
right. Okay. So before closing, I request the speakers to sign the video release forms. But yeah, any more questions for Victoria? Okay. So if not, then let's thank all the speakers.
Thank you.